Okay, the next speaker is Dr. Harn, whose research interests in life cycle sustainability assessment of building materials and the technological aspects of bio-based building materials. Dr. Kuo has authored about 100 articles in these research areas. The sustainability assessment model that he created can measure the level of vulnerability and resilience of the life cycle of materials or systems under study. He has won more than 50 different academic awards and delivered more than 50 invited speeches around the world. He is currently involved in research collaboration with groups in China, USA, Italy, Colombia, South Africa, and Saudi Arabia. Okay, Dr. Kuo.
Thank you very much. For those of you who may not be from Singapore, welcome to NUS, welcome to Singapore. Great to have you. And definitely it's my pleasure this afternoon to be able to talk on a subject which complements the scope of what has been covered by the speakers earlier on. And I'm talking about a story of biochar, something which is at the level of materials. So we are going to look at how different kinds of materials can actually help us to accelerate development in 3D printing, for concrete especially. This is something that has been alluded to many times today already, and that is the appropriate material and more specifically, the rheological properties of materials for 3D printing. So I'm not going to go through this again. Basically, it is all about being extrudable, buildable, and of course, it must have high shear strength, compressive strength, and of course, to be adjustable. Adjustable in terms of the setting time and hardening time in the case of concrete. And I think more importantly, which I'm happy to read about, which was actually mentioned in this particular article, is the use of local and low-cost material. And I find that if we are able to add one more line to that, it's even better. And I'm referring to the use of waste material. Waste material is everywhere, right? In fact, having done different projects on waste, including food waste, which I'm going to talk about today. Just now, over lunch, I was a little bit concerned, and I was always looking around, especially into the dustbin, to try to find out whether we have been throwing away too much of the food that we can actually eat. So let's look at some statistics. I mean, I'm not terribly proud about all these numbers of the amount of food waste and wood waste that we as a country generates every year. Not to mention that our recycling rates for food waste is not very high. It's about 13%. So can we do something about it? Of course, I'm not trying to say that the technology that I'm going to share with you is going to improve that number, okay, by improving that, increasing the recycling rate many folds, but I see that as a potential in the future. So this is what typically we see, and I'm not going to go through the details here about how much we are producing every year and how much of those that we produce is recycled. But let's talk about whether we can come up with a technology that in the first place can help us to recycle agriculture. Yes, we do have an agricultural industry in Singapore. Many of you not from Singapore may not be aware of that. So can we do something to recycle the agricultural waste and also food waste for construction? At the same time, do a bit more to improve the tunability, the adjustability of material properties for 3D printing. So here we go. What is biochar? Biochar basically is a solid byproduct of thermal decomposition under very special condition. And some of you may actually identify this term called pyrolysis. So these are just some pictures about what biochar looks like. Basically, it's almost like charcoal. The only difference is the conditions under which it is produced. There have been a lot of studies already about the pros and cons of biochar and the fact that it is widely considered as a carbon negative material. Of course, that is provided that we are able to evaluate the amount of carbon it can sequester as well as to take in throughout its whole life cycle. And these are just some of the major benefits identified for biochar? Well, a little bit of history about biochar. It is more of a material that is being adopted widely for agriculture, for soil remediation, for example, as well as the removal of pollutants in water. And now we are pushing for using it as a way to remove pollutants in the air. But of course, before that, we have done a lot more work excuse me, by using that as an additive in concrete. So what's the big deal about biochar? So I'm going to, with only a few slides, this is going to be quite a short presentation, to introduce to you some of the desirable properties of biochar, which actually holds relevance to 3D printing. But before that, let's take a look at the size distribution of the grain. And of course, this is linked to the morphology. And these two pictures are taken using special technique known as scanning electron microscope, which shows you that the particles of biochar is highly porous. Now that itself is interesting because that, if used appropriately, can help us to tune the rates of hydration of cement and therefore even speed up the hardening or setting process, something which is quite desirable for 3D printing. And of course, if the feedstock is different, the morphology is going to be different as well. And that explains why we have different types of grain size distribution. So moving on, these are some of the key results that we have found. And over here, you see the comparison of the compressive strength of mortar containing different types of biochar. And by that, I mean wood waste, food waste, and rice waste biochar. And in case you're wondering, yes, we do throw away some portion of the rice that we eat today. So I hope that after my, my presentation today, even if you cannot remember anything that I said, please remember not to throw away your food. So, what's the message here? The message here is that if you have biochar added into the mortar, you find that the early strength actually goes up. But of course, the extent of increase is where the tunability and adjustability lies. So if we can, and I'm confident about that, adjust the amount of biochar that we use, as well as to make use of different kinds of biochar, we might be able to bring it down to that delicate degree of adjustability. So this is for the 28-day strength, and what we have concluded is that the increase in strength is caused by the absorption of water, and of course, the gradual release of the absorbed water into the medium to support further hydration. And that's not just what biochar can do. We find that the water absorptivity, as well as the water penetration level of mortar containing biochar, gets controlled as well. And by that, I mean it gets reduced. So as you can see from this graph, the lower the bar, the better it is. Because the lower it is, the lower the water absorptivity. That means that basically, in layman terms, it is more waterproof. Of course, conducting all these experiments and getting and making sense out of these results are definitely important. But what I think is equally as important is for us to have a very accurate understanding of the theory behind all these phenomena. So we have just created a model that allows us to actually imagine what happens when pores are formed in biochar as the result or in the process of pyrolysis. So you can imagine that we have two pores in the biomass, and in the process of the pyrolysis, these pores expanded, combined, and become what we call a pore cluster. And then, if we are to use this model and imagine how these are actually present in the actual mortar containing this very porous material called biochar, which is basically quite similar to this, and you consider furthermore a local region like this and how that particular region can actually bubble off. Now that's my own term, we call it the bubble off, and that's why it is known as the pore wall bubbling model, which is more realistic because it is about non-uniform and localized expansion of the pore wall. And then after a few equations later and many sleepless nights trying to derive finding the bug in the computer modeling, we find that, hey, it seems to be able to describe what we found pretty well. So over here, we have done simulation and we have done our calculation and tried to match our theoretical prediction, which is in the form of dots and crosses here, okay, and see how they actually match the actual experimental data. We find that the match is not too bad for 300 and 500 degrees Celsius, or rather biochar made at 300 and 500 degrees Celsius. And of course, using the data, we managed to find certain things which can actually be verified. We are still in the process of doing so, and that includes, for example, the number of pore clusters in a sample of about 10 grams of biochar. So this is the number that we have predicted. We are in the process of verifying that. We even uncover certain characteristics not discussed anywhere in the literature, which includes, of course, what we call the R critical, and of course, the minimum size of the pores that can be described using this model. In conclusion, all right, we have in a way shown that biochar as a building material seems to be a pretty effective way of recycling the kind of waste that we have, all right? Ultimately, nothing can be as local a material as the kind of waste we produced, and that mortar containing biochar has a higher early strength and low water absorptivity. And I think that can actually cover or open new doors or possibility for us to tune mortar containing biochar and see how it may work better for 3D printing. And of course, last but not the least, a theoretical understanding of how the pores are developed, form, and evolve is very important because it will then allow us to choose the right kind of production environment as well as feedstock in order to produce the kind of biochar that we can further tune in order to improve the quality of 3D printing. So this is where we published our result not too long ago. Suradip, maybe you can identify yourself. He has done a lot of good work in this area. Okay, he's in our team. Okay, good to have you. And of course, the rest of my guys here, they are now clapping. So, okay, this is us. Mani is here. Chakri. So, basically, we were the center of the world's attention for maybe 5 minutes. Okay, after taking the photo, that's it. All right, so this is where we are, or where we were in the lab, showing off our invention. And of course, all right, let's play a little game here. Okay, what do you think that is? Oh, we have Swiss cheese coming out. You know, that's a good thing about doing material research. When you get down into the minute, when things become boring, you try to imagine certain things to spice your life up. Okay, any other suggestion? Ice. Okay, this is basically a pore in biochar, right? If you look at this deeper, I don't know what you see, but I see this guy. Beethoven. So that's the thrill of doing biochar material research. It thrills you, maybe because of your imagination. But anyway, what's that? Yeah, that's right. Maybe it's just some illusion, like what I said. This research won't be possible without MOE and, of course, NRF through their Intra-Create Seed Collaboration Fund. And, of course, that's it. Thank you very much for your attention.